Hi and welcome to this video for the BTEC Applied Science Level 3, Unit 19, and this is for Assignment 2. So one of the pass criteria, the same way as with the carbon-13, for the proton NMR, you will be given a selection of molecules and some spectra, and it's a case of matching the molecule to the spectra and given some reasons why in terms of their a number of peaks, the number of environments, the chemical shift, integration values, and splitting. So we've got a selection at the bottom here. I've doodled them out just in skeletal form, just in case you would have some trouble reading them out as they're listed at the bottom. And we've got the table on the right, so you would have that to hand, and a few of the spectra up here. So you can see we've got more molecules and spectra, so we need to try and cancel some out before we start looking to working out which of the remaining four match these four. Now, the first thing I would do, again, you can do this quite laboriously, where you work looking at your molecules, actually determining the chemical shift, splitting, integration values of all of them. But to try and save a few minutes, first thing I would start with is actually look at the number of environments of each of these, because as we can see, we've only got either a 1 environment or a 2 environment spectra there. So if any of these had 3, 4, etc., we could quickly cancel them out. So for here, we've got 2, 1, 3 in there, 1, 2 there, got 1, 2 there, 1, 2 here, and 1, 2 there in terms of the environments. I've done those very quickly. With regards to the alcohols, the hydrogens on them are an environment. There's what you would usually see if they were present here is a little peak, and it tends to, above it, have this peak disappeared upon the upon the addition of a D2O shake. So I'm fairly confident none of these will probably be it. There and there. It's just a bit of a tough addition. So we can see none of them. We've got 4, this one's got 3, none of 3 peaks there, so I can instantly rule that out, don't need to bother with it. And we've only got one of the molecules here that's got 1 peak. So we know this is going to be spectra A, nice and easy. We can see with the fact that it's 3 lots of CH3s, there is no hydrogen on this middle carbon, then these would all be singlets, which match this being a singlet. In terms of their chemical shift, best guess is kind of between this RCH3, the 0.7 to 1.2, and the CH2Cl. So the bromine isn't directly on the same carbon as the hydrogens. It's very close to it though. So this RCH3, the 0.7 to 1.2, you can see it's being shifted a bit up past that 1.2, a bit more downfield, since there is an electronegative atom nearby. So there isn't sort of anything that perfectly matches this, but that's what we could say as a comment for it. The 0.7 to 1.2 shifted a bit more downfield due to the nearby electronegative atom. Okay, so A is done there, match that one up, tick. Now in terms of the others, all of these have got 2 environments, so fairly tough to match them out. Now, what I like to look for, these triplets, quartets, they're quite nice to spot on spectra because the easiest way to generate those is a CH3, CH2 next to each other. And this X doesn't have any hydrogens, so the CH3 becomes a triplet due to N+1. So the 2 hydrogens there, 2 plus 1, turns this into a triplet. And the 2 hydrogens on CH2, 3 hydrogens next to it, 3 plus 1, turns this into a quartet. So what I'm looking for is the CH3-CH2 little chain. As we can see right at the start here, CH3-CH2. Check the others to make sure. CH3C. Here we've got a CH2CH, CH2C, CH3C. So this is the only one that matches. So as I was just saying before, this would be the triplet. This would be the quartet. CH2 there, CH3 here. In terms of the chemical shift, CH3 next to an R group, 0.7 to 1.2. Again, a little bit more downfield than we'd expect, but we've got this nearby iodine there, so electronegative, pulling it a bit further than we would expect to see. CH2, we've got in the table here chlorine or bromine. Iodine's electronegative as well, so we can have a guess that it would be in a similar range, the 3.1 to 4.2, which it is. So it's a bit less electronegative than these two, which is why it's down at sort of that lower 3.1 end. So again, with this, I could write a justifiable comment that it's a bit past that range due to the nearby electronegative atom. So 2 of them done. Now, B and C, so we've got how many? 4 options left. 2 of them will match up with these. Both are singlets in there. So what that means is the hydrogens cannot be next to the carbon with hydrogens on it as well, otherwise splitting would occur. So here, because we've got the CH2 next to the CH, these would split each other. So we'd end up with a doublet there and a triplet here. So I can rule that out. So this would not fit either of them. These would be singlets around there because the CH3 is just carbon there, so no splitting. And here, CH2 next to C and CH3 on that end. So again, these two environments aren't going to be split. Across here, CH3, C in there. Again, as we can see, there are no hydrogens on adjacent carbons for either of those two environments and no splitting there. So we've got 3 molecules, 2 spectra left. Now, in terms of these, what I'm going to do is rule this one out because I have not been told that either of these disappeared upon a D2O shake. Also, the fact that the size of them in terms of the ratio look a little more even rather than this 1:9 ratio that we would have here. That's a 1:9 hydrogen ratio. So my integral lines, one of them should be, 9 times the other effectively, and they do not look anything like that. So I'm going to disregard that one. I could have checked for the chemical shift as well. So the CH3 to the R there, the 0.7 to 1.2. Hydrogen between 0.5 and 5 to little peak appears more or less anywhere in that range. So with these, to determine which way around they're actually going to go, these bromines, we can see looking fairly similar. The CH2 environment's next to a bromine there. The CH3 is adjacent to a carbon with a bromine. Whereas here we've got the CH3s adjacent to a carbon with a bromine and CH2 directly connected to a bromine there. So that's fairly similar between them. So to try and distinguish it, what we can have a look at is the integration values we'd see for each of these. So with this, we've got 4 hydrogens in the same environment and 3 in this environment. So we've got a 4:3 ratio. Whereas in this one, we've got 6 hydrogens and 2 in there. So we've got 6:2 or a 3:1 ratio. So if we look at our integral lines, we can see these are roughly equal. This one on the left a bit bigger if I kind of sketch that along, since it looked to be starting at roughly the same point. So that's going to be our 4:3 ratio, whereas down here you can see this one is much bigger than this line. So we've got the 3:1 in there. And then we can match it up. So this environment there, the 3:1, that's going to be the CH2 directly connected to the halogen. That's the 3.1 to 4.2. And this is going to be the CH3 to R, 0.7 to 1.2. Again, shifted downfield because on that R group, there is the highly electronegative atom nearby. And then for this one, for this environment, the CH2s, so we've got 2 CH2s connected to the bromine in the same environment, 10 to the 4. Same range, 3.1 to 4.2. And CH3 in C there, so R 0.7 to 1.2, same comment as before, nearby electronegative atom, pulling it a bit more downfield than that 1.2 we'd be expecting. So this one was B, and this one was E, and there we have matched up the 4 spectra to the 4 molecules, and that's kind of what you'll need to do for the pass criteria. Thank you.